So we are talking about machine intelligence, so humans should be more intelligent. So let's fill that seat. That's okay. So what I do is that I'm loading, so let me just run this demo. So what I'm doing is, so there's this ovarian cancer data set that's out there, so I just load it, and I just see what is in that data. So let's see that. So, sorry. So what we have is that I have an observation matrix. I have 216 examples with me. I have 4,000 features. So N is 216, D is 4,000, still not large scale. It's pretty small scale in the sense. And then I have a group, so this is my observation matrix, and as I said that I already have complete annotated data, so I have the assigned group. So each patient has an assigned label to it, and it's a classification problem. So it's a classification problem, so there's a label assigned. So when I look at the group, sorry. So I see that it's a binary classification problem. Either some of the patients are characterized as having ovarian cancer, and some are normal, some are healthy subjects. That's what I want to do. So now what I'm trying to do is, so I have a training data. Now I want to know, how do we train our model, and how do you verify that my model is good or not? So one thing I know, that my testing data should not be visible to the model while it's learning. So what I do, I partition my data into training data and testing data. So that's what I've done. So it partitions it into 160 training samples out of 216, and what I end up is 56 testing samples. So that's what we get here. So okay, so we have a training sample. On this training sample, I'm going to train my model, and this testing data is basically the sort of a novel data which is not visible, and I randomly selected. So there was no, that's another aspect of unbiasedness. There's no deterministic thing that is going on. I randomly selected any 56 out of these 216 subjects. Now, and then I just say that this is a data train. So that's the X matrix, the observation matrix. This is the outcome, so group train. So whether it's normal or abnormal, so it's a binary classification problem. Now the point is, I want to learn the features. So there are like 4,000 features. या तो हम ये कहें कि these 4,000 features completely describe everything, every patient, and I can just use it. And I say, okay, I'll use all these 4,000 features without any dimensionality reduction, and I'll say all these features are representative of what is happening, and I'll be happy with it. But again, these features could be redundant. These are not the most significant features. This is not the most compact model. There could be noise in those features. So I want to select the most prominent, most significant features that can be representative of my model. So that's what I want to do here. So what I do in the following, that I break this training data into two groups. So one which is normal and one which is cancer. So I just split it. So I had this 160 samples. So I had this, so the new matrix was basically, so my training data is now, basically now 160 by 4,000. That's what I have now. So I've splitted this 160 into one group which is all normals, because I already have annotations for that, and one which is all cancers. So that's what I've done. And I do a pairwise t-test. That's what I'm doing. So t-test is actually computing, it's doing a statistical analysis of each feature. So the first feature with all the remaining features, the second feature with all the remaining features, so I can get a rank. So it tells me the level of significance. So what I'm getting in this case now is the following. So when I run this t-test here, so this p matrix, this p vector, these are the associated p values for all my features. So I have 4,000 features. And we know from statistical analysis that if p is less than 0.05, it is statistically significant. So all those features, out of those 4,000 features, jitne bhi features hai jinki p value statistically significant hai, these are my most significant features. And I'm going to keep those features, and I'm going to discard every other. That's what I'm trying to do. So there's a filtering process. I don't want to use all my 4,000 features because they could be noisy, contaminated. Yeah. It could be anything. It could be anything. It could be tumor size. I don't know. So that's a good question. I don't know the name, but it could be anything. So for example, in the problem that we are doing, we have tumor size, we have tumor shape, we have mean, we have standard deviation, we have heterogeneity, we have texture, we have intensity. There are so many features. You could always go for as many features as possible. There are lots of features. In fact, our library, I think Faizyab and I, we are working on this thing. We have like close to 1 lakh features that we have actually started with, and we're trying to filter it to 154 features. So it could be anything. So here that's not the main thing. So we are trying to say the main thing is I want to filter the feature set so that I get those subset of features that are statistically significant. So that's what I do. And the first plot I do is that I plot a cumulative distribution for this p-values. Let me see if I could. So this is what I have. Sorry, so it's not that thick line, but I've just so that it's visible. So that is basically the cumulative distribution of my p-values. And what it is showing me, there are lots of p-values which are close to 0. And below 0.5, they're close to 50% of features which have p-value less than 0.5. That's what we have. This is a cumulative distribution, so it should sum to 1, so it goes to 1. So that's what we have. So not all features are relevant for us. So I'm only going to select those features which are actually statistically significant, and that's what I do here. Sorry. Okay. So now I do feature selection using supervised learning. So I had this p-values for all those 4,000 features from that 160 training samples. I sort them in increasing order. So the smallest p-value is at the top, which means it is the most significant. That's what we have. So I've sorted my p-values here. Now so I want to understand now that which features are giving me the lowest classification error, misclassification error. And for that, I use the test data. So agar aapko yaad ho कि 260 का data था हमारे पास, and then we splitted this thing, so the testing data is now 56 times 4,000. That's what we have. So I'm now going to say that given this test data, what are the set of features that gives me the minimum misclassification error? That's what I want. So एक तो हम ये भी कर सकते हैं कि हम ये कहें कि अच्छा भी हमने already sort कर लिया यहाँ पर, let's select the top 10 features. Let's select the top 20 features. But maybe the first and the 10th feature are highly redundant. They are very correlated to each other. So they are not giving me any unique information. So I want to keep those features that are impacting my classification error. So that's what I want to do. So I have this very simple classifier. It's a quadratic classifier. It's a quadratic discriminant analysis. It takes a training data and a testing. It takes a complete training data. So you have the training observations and the training annotations. You train a classifier, a quadratic classifier, and you test it on the separate test data that we have. So once you have the test data, what you do? You actually, so this thing here is actually telling me a classifier, and then it is classifying, it is predicting. So wait a minute. So it trained a quadratic classifier based on this, and then it tested the outcome of this X text, and then it compared it with the truth. That's what we are trying to do. So we train a classifier, a quadratic classifier. We also gave it a test set to tell me what is the predicted outcome based on what the training that you have done. And then compare it. So again, we are comparing its classification now. So it has to be a comparison. It cannot be a mean squared error. This is a classification problem. That's what we are trying to do. So now what we do is that we say we are going to select 5 features, 10 features, 20 features. So we are just doing that. We could do incrementally also, but just to save time, we are doing this thing here. And then we do a cross validation. So a 10-fold cross validation that we are trying to do, and what we end up is basically something like that. So this is what we are trying to see. So when I look at the misclassification error by resubstitution method, which is not the best, we see that the misclassification decays to, it's close to 0 when we have 40 features. So 40 features and you've attained perfect classification on this one. So that's the training classification that we have. But now when we test it on this novel data, we see that it is decreasing by the 15th feature, but then it shoots up. That's overfitting. That is basically overfitting. Because now I'm not happy with this performance. I'm saying this misclassification is not good. I want to decrease it further. So I start pulling in more features as I go. But what I'm trying to do, I'm trying to chase my performance now. I'm trying to chase my training performance now. That's what I'm trying to do. And that chasing the training performance, it is no doubt reducing my training error, but my testing error is blowing up. So that's overfitting. So we have to be very careful. So we can't just keep on adding more and more features just so that we want to see that ideal number where my training performance is exactly 0, because that may not happen, and that's not even desired. We don't even need to stretch ourselves so that we compromise our performance or prediction on unseen data. So that's what we have here. Ji. Yeah, we trained it. So in this code, so this is a training. So what we are trying to do is, so in this case, we train a classifier based on these annotated data. It's a quadratic classifier, and then we predict on this testing data. It gives me a predicted outcome. So once you have predicted outcome, we compare it with y-test. This is a string compare. If it is similar, it will give me 1. If it is similar, it will give me 1, and there's a negation here, so that's 0. If this is different, that is 0, this is going to give me 1. So what it is saying, so jahan is vector ke andar 1 hoga, it is indicating, it is flagging that these are the patients or subjects that are misclassified, and I sum them. That's what we have. So that's what we are trying to do. And you can have any classifier. You can write your own classifier. You could have a SVM classifier. You could have a logistic classifier. You could have your own cost function also if you're interested in. So there's a very, very simple supervised learning example where I'm saying iteratively selecting my features, where my feature selection is guided by my annotated data. So that's basically feature selection for classification using supervised learning. No, sorry, which feature, sorry? Which feature set? So I'm not going incrementally, just to save time. I looked at the first 5 features. मैंने पहले 5 features लिए, मैंने उनकी classification performance निकाली. एक चीज आ गई, I got a point on the curve. Let's say here. I got this point on the curve. फिर मैंने पहले 10 features को देखा. I get this point. फिर मैंने पहले 15 को देखा, and so on and so forth. So I'm augmenting my feature set. This is not the only way, by the way. This is not the only way, but just to illustrate an example. You could come with your own novelty, with your own interesting ideas. But we are saying we are augmenting our feature set, and we are going to see कि कहाँ तक मैं जाऊँ so that I get a good training performance and a good testing performance. Yes, sorted. So these are the sorted features. So we have already sorted it using, so if you see here, so these are sorted. So हमारे पास p values आ गई. Now we have sorted them in ascending order. तो जो सबसे पहला feature होगा उसकी सबसे lowest p value होगी, which means it is highly significant. So even we are selecting top 5, but there's a logic behind it. So the logic is that we select the most significant features based on pairwise t-testing, and then we actually augment further and further and further and see where do I break down. So that's what we have. Yeah. Again, this is not the best method, to be honest. So resubstitution is not. Yeah. Yeah, so we are saying according to this, my minimum, okay, if I look at red line, let's say we did not have a blue line. We see 40 features is good enough, let's say. The top 40 features are good enough, it is giving me the minimum misclassification error, and I'm happy with it. But when I see the testing data now, because this was just the training performance, I see that the 40 features are giving me far worse classification than the top 15 features. Because now, if I just look at the red curve, I'm chasing my training performance. And I'm compromising on overfitting. I'm compromising on generalizability. I want my learned model to be generalizable. And for that, I need to look at the performance on unseen data, and that's one way to actually solve for overfitting. I've already mentioned in advance. There is a cross-validation or a validation. So this validation, cross-validation, what it does, it breaks your data sets into 2 subsets. One is a training data, one is a testing data. The testing data is not seen by the model, but you have manual annotations for both. You have the true annotations for both. And you actually use your testing data to guide your learning. And that's a supervised learning. We don't know. We don't know. There is no answer. There is no answer. We don't know what to go. Should we have stopped at 50, 60, 70? We don't know. These are number of features. जहां पर मैं कर रहा हूं 5-5 का ग्रुप ले रहा हूं, 3-3 का क्यों नहीं ले रहा, 4-4 का क्यों नहीं ले रहा? This is just an example. There is no rule. So there is no recipe that you go and cook it like that and you're going to do for all your problems. There is no recipe. So he's saying that how many iterations we have to do. So here, just to save time, I'm actually incrementing by the first 5 features, the first 10, the first 15, the first 20. But you could ask why 5, why not 4, why not 6? There is no answer. There is no answer. It depends on the task. You have to learn through that. So this is called parameter optimization, and these are how do you optimize your whole algorithm. There is no like fixed recipe for that. So that's something that is open. Okay. एक मिनट, सॉरी, मैं अब आपकी बात काट रहा हूँ. जो आप जिसको 100 iterations कह रहे हो ना, 100 iterations के बाद मैंने 500 फीचर कर लिए, let's say मैंने, but let's say you are incrementing by 1, आपने 100 में सिर्फ 100 फीचर्स किए. So iterations का यहाँ कोई ऐसा कॉन्सेप्ट नहीं है. It could be like, what if somebody said, I will take the first 10 features and then increment by 10, 20, 30, 40, उसके लिए 5 iterations लगेंगी. It's different. So iteration, so don't get driven by that iterations thing right now. So I may be wrong, but iteration does not hold any significance right now in this example. If I just change it to 1, 1, 1, increment by 1, there will be far more iterations. So yeah, so that's nothing, there is nothing too like fancy about it. Ji. It has to do? Yeah, so that's a good point. How do we know whether it's overfitting? We have to iterate more. So how much do we have? So we don't know in advance, that's what I'm saying. No, we don't know in advance where to stop, how far to go, we don't know. That's all what I'm trying to say. And this is a very, very simple example. This is not a large scale data set. It's a very, very small scale data set. All right. So now I'll show you another example, which is basically a demo on logistic regression that we are trying to do. So this was classification basically. So in logistic regression, what I'm doing is the following. So I use again this Fisher Iris data set that I had shown for overfitting. So when I look at it, so let's see this thing. So it has 150 measurements, so 150 by 4. So you have 150 examples, and each example is a 4-dimensional vector. So the first column is the sepal length, the second is the sepal width, the third is the petal length, the fourth is the petal width. So 150 by, so you have 150 samples, and the 4 columns are representing dimensions of sepals and petals. That's what we have here. And we have 150, and species, so you have a label that has been assigned to it. So if you look at this thing, so we have 3 labels, Setosa, versicolor, and virginica. These are the 3 species where we have drawn these samples from, and the features are basically dimensions of my sepal and petal. That's what I have here. So now the first thing that I do is, because I'm doing regression, I need to convert these labels into some numerical value. I want to get a nominal response. So what I do is that for each class, I assign a value, whether it is 1, 2, or 3. So all what I'm trying to do is now is I'm trying to reformulate my classification problem, my labeling problem as a regression problem. So I had these variables Setosa, so these are like verbal descriptions of my species. And I assign now these numerical or nominal response variables to these classes. That's what I have. And now what I do is, I do this very simple command, which is a multinomial logistic regression. It takes the observations